From yesterday, we were talking about complex numbers, right?
Yeah.
So let's review this real quick. So we said that the set of all possible numbers is the set of complex numbers. And complex numbers in standard form are written as a plus bi. And usually, this is kind of odd, but usually the variable we assign to a complex number is z. Okay, so we'd say that if we've got some complex number, it's represented by z. It's in standard form is in the form a plus bi. So what do we call a?
What do you mean?
Remember? What do we call a?
Oh, it's the real number.
It's the real part,
Real part.
right? Good, it's the real part. What do we call b?
I'm looking
The
at
imaginary.
Oh yeah, pure imaginary.
The imaginary part. Okay, and so we said then that really we could summarize the set of all real numbers, the set of numbers up until about a week ago, the set of numbers that we had used exclusively throughout your entire lives. That was really just summarized as the set of complex numbers where the imaginary part is equal to 0, right? So that's just where b equals 0. The set of pure imaginary numbers would be the set where the real part is 0. And most complex numbers are going to be a combination of both, okay? So for today, we're gonna do kind of the goal for today is we want to understand how some ways we can represent complex numbers. This isn't really in the textbook. This is kind of a little extra stuff for you guys. And then we're going to start to look at how we do arithmetic with complex numbers. It's different and it's a little bit more complex, pun intended, than dealing with real numbers. Real numbers are pretty simple to add, subtract, multiply, and divide. Complex numbers, there's a little bit more to it, and we want to get used to doing arithmetic with these new kinds of numbers. Okay, so one way we can do this, that we can represent complex numbers, is in what's called the complex plane. Okay, and this is, once again, this is not really something that's a normal Algebra 2 topic, but I want you guys to be familiar with this, because you'll deal with this a lot in the future. So the complex plane looks just like the regular xy plane, but instead of the x-axis, we're going to call that the real axis, and instead of the y-axis, that's the imaginary axis. And then all we do is we're just going to plot, for any complex number, we're going to plot the real part acts like the real coordinate, so it's like an x-coordinate, and the imaginary part is the imaginary coordinate, so it's like a y component. So for example, if we had the complex number z equals 4 plus 3i, what's the real part?
4.
What's the imaginary part?
Yeah.
3. Okay, so then just 3, right? The imaginary part is just the coefficient of I. Yes, Jim?
So you could kind of think about this as I equals ax plus b.
Well, I mean, it's kind of, what do you mean by that?
I mean, just to represent numbers on that graph.
Well, to represent numbers, yeah, really all you're doing is you're thinking about these as just ordered pairs. So the position of the number 4, 3, which corresponds to a real part of positive 4 and an imaginary part of positive 3, which is that complex number, would be there on the complex plane. It would be the one that has coordinates 4, 3. Okay? There's two ways we can represent that, even given that position. Most of the time, we like to represent complex numbers as vectors. Have you ever even heard the word vector before?
I've heard it,
Yeah.
but only in
Really?
Okay, say something about it. Kid, tell me about a vector. What do you know?
Magnitude and
That's
direction.
the guy's name who's looking at me, that's
Oh,
all.
okay, there you go. Okay. It's got, say it again.
Vector.
Okay, a vector has magnitude and direction. So a vector quantity in math, or more importantly, probably in physics, would be a quantity that requires some directionality. Now, as opposed to a vector, there's two kinds of quantities that we talk about in physics. There's other kinds too. But we talk about vectors and scalars. If you remember what a scalar is?
A scale.
I just remember I said that
Is
before.
it
Okay, this is good science review. Raise hands if you got, if you're going to contribute, raise hands. Scalar is a quantity that is represented by a number only. So an example of a scalar would be the temperature of the room, right? All we need is a number. If I say, what's the temperature, and you say it's 72 degrees Fahrenheit, that's all I need. I don't need a direction, right?
So that's like when you put, like you step on a scale, like the old ones, you can range that number, that set number.
Yeah, it's a set number, right? So if I want to know what page you're on in a book, I guess you could call that a scalar quantity. The number is sufficient. What's an example of a vector? It's got magnitude and direction, but what's a quantity? Can you tell me a quantity that would require you to use a vector instead of a scalar? What's a quantity?
Speed. I don't know.
What would it be?
Speed? No.
Okay,
Miles
speed,
per hour.
well, okay, close.
Coordinates?
Close.
Knots?
I'm just
So speed is actually a scalar. Now, hey, don't talk. Raise your hand. Yes, say, please raise your hand. Do we get too many side conversations going on? I can't communicate with everybody effectively. So, hold up, 1 second, hold that. Speed is a scalar, and here's why. Because when you're in your car, if I ask you what's the speed, all you have to do is look at the speedometer and tell me a number answer, and that's sufficient. Okay, question.
I was gonna say, does it have to be like a set?
For a vector? I don't, if I understand what you're saying, the answer is no. I bet you'll be able to answer that question for yourself in just a second. Yes, sir.
So like velocity?
Like velocity is a vector.
I said that.
Okay. So velocity is a vector because velocity requires a direction, right? It's different. Like if I'm walking, if we want to do velocity just in one dimension, let's say we're just going to do velocity in a line along the front of the room. We could say that that's the positive direction and that's the negative direction, right? And there's a difference. If I'm walking, if I'm covering 1 meter every second, this we would consider to be positive velocity because I'm moving in the positive direction. This would be considered to be negative velocity because I'm moving in the negative direction, right? So velocity is different. If you change your, like say you're driving in a car, if you had a velocitometer instead of a speedometer, that would be a little bit confusing. Because then it would always be constantly giving you your speed and the direction in which you're traveling, right? We don't necessarily need all that information all the time. I mean, we can see where the road goes, we follow the road, we really just need speed, right? If we were traveling, and let's say we started off going due east at 70 miles an hour, and then we went through a turn and we ended up going due north at 70 miles an hour, we haven't changed our speed, but we have definitely changed our velocity, right? And the proof of that is, well, I don't want to put too much of this, but it requires a force to change your velocity. There had to be a force there. You had to have friction acting on the tires of your car to be able to make that turn. If you were trying to do it on, say, a sheet of ice covered with WD-40, then you couldn't do it. Your car would go straight even though you turned the wheel, right? Because the ground wouldn't be able to impart a force to the car to make it change its velocity.
So you
right?
need friction?
So you need friction if you're in your car to do it, yeah.
I just love that.
Okay, so anyway, that's a vector quantity, right? So vectors require both magnitude and direction. A lot of times, is this number a vector quantity in that sense? Not in an obvious sense, not like velocity is, but a lot of times we like to represent complex numbers as vectors because the length of the vector tells us the size of the number, right? The size of the complex number. And the direction tells us something important too. And when you start to get into like more advanced topics in complex analysis, dealing with complex numbers, you can represent lots of things like multiplication, division. You can represent all kinds of things by just using these vectors. For example, if we want to add two complex numbers up, you can add up the vectors, and you always add vectors. You'll talk much more about this in the future. You always add them tip to tail. So if I had another vector, let's call it Z2, and Z2, let's say we had another number here that was, it was this guy right here. So the number in this case, the real part was -3, and the imaginary part was 2, and I wanted to add those up. I'm going to see, when we get to adding complex numbers, see if you can make sense of this. If I want to add those vectors up, I could just put them tip to tail. And this is what we call the resultant. This would be the sum of, whoops, wrong color. This would be the sum of the two. Wherever I end up there would be the real part and the imaginary part of the sum of those two numbers. That's way above and beyond anything we have to do in Algebra 2, but I wanted you to see if you can make that connection when we talk about how to add complex numbers. We'll come back to this slide and see if that makes sense.
Of the 2 points?
Yes, if I wanted to add those two numbers, like if I was adding, we'll call that Z1, and if Z2 was -3 plus 2i, when I add those up, does it make sense that I could add this vector and that vector, and if I add them tip to tail, whatever the coordinates are there, that's going to be the size of the vector that we get when we, the size of the number we get when we add those complex numbers up. You'll see a connection when we get to that point, I promise you. So anyway, this is our way of representing a complex number in a way that's visual, that gives us some additional information. Yep.
So if you're measuring that as if it was velocity,
Mhm.
so if you added those two together, the total velocity of the entire amount of time was equal to the orange line?
It would equal, yeah, it would equal that one. Yep. Mhm. That's correct. That's correct. That'd be the sum of the two, is what I'm saying. Yeah. Okay, so now, here's another way to represent it. Sometimes we just represent it as a point in the plane, right? And we just think of it as being the point relative to the origin, but the vector really is better. So could you identify real quick, don't say it out loud, but everybody see if you can pick this one out. What's the complex number representation in the complex plane for the complex number -9 minus 7i? Which one is that? Which vector represents that?
B. Oh. I don't know if that's even right, so no.
I'm going to tax the first one.
Sorry.
Well, it's all it is, right? It's just going to be the one that ends on the point in the complex plane with what coordinates? -9, -7, right? The real part, what goes on the real axis, the real part is -9, so I'm going to go back 9 horizontally, and the imaginary part is -7, so I'm going to go down 7, and so it's going to be V.
What's the I gonna
Well, isn't it?
The I is just the imaginary part is just the coefficient of I, right? So like in this last example we looked at, the real part is 4, the imaginary part is 3. And so therefore the coordinates in the complex plane that correspond to that complex number are 4, 3, over 4 up 3. Okay, see what I'm saying? Okay, everybody get that? I know it's kind of strange, but that's not a difficult concept. It's just you probably are wondering, why do we do that? And you're not going to fully appreciate that now. There is something we're going to do probably next Wednesday. I'm going to show you an example where you can kind of get an appreciation for this a little bit. We'll do an electronics example. That's kind of interesting. So the answer here then would be V, right?
Yep.
Everybody see that?
Yep.
Okay, because the coordinates of that point are -9, -7.
So, when you talk about the item difference, so yesterday with like the negative,
Mhm.
that doesn't go to.
I mean, it's all related, but this is something, all we're doing here with this is we're just trying to, how do we represent that complex number in the complex plane, where this is the real axis and that's the imaginary axis? That's it. Okay, I'm showing you a complex number in the complex plane, and now I want you to tell me, what is that number? Don't say it out loud, but everybody think about that for a second. So you have to just think, a complex number in standard form is always in the form z equals a plus b times I, right? A is the real part, b is the imaginary part. Okay, so Kaylee, what's from that picture, what are the coordinates of the point that's represented? Other way around, good. Okay, so -4, 0. What's -4 represent? The real part, and 0 represents? So then what is that complex number? -4 plus 0i, and what's 0 times I? Okay, so that's the number -4, right? Okay, you make a connection there? All real numbers are just going to exist on the real, we call it the real line. You ever wonder why we call it the real line? That's why. It's the real line because that's the axis, the real axis in the complex plane. So you used to call it the number line in like 3rd grade, and then after a while you started to call it the real line. That's the real line. Every real number sits on the real axis in the complex plane, right? Okay, let's try another one. How about this one? Okay, what's going to be the complex number corresponding to that vector in the complex plane?
7-1.
So the coordinates are what?
7,
7, 1 it looks like, if you look at the axes carefully, right?
Oh, great.
So you're going to get 7 plus 1i, so just 7 plus I. Okay?
Up into the
Is
wall.
I one?
The coefficient of I there is 1.
Oh, so it's like.
Remember, I is the imaginary unit. What's I equal to? Square root of negative 1. Yeah.
So when it is, well, it's like we wouldn't write 1x. So
No, you're right, you
we
wouldn't.
just write x, and so we just write 1. I mean, I.
Exactly. Did everybody see that point? So we wouldn't write 1 times x. We wouldn't write 1 times x. We literally just treat I like a variable. It's not a variable. It's a constant, right? It stands for the imaginary unit. But you treat it just like a variable. So you wouldn't put a 1 in front of it as a coefficient, right? That's implied. Okay, so the one other advantage of this is when we use the complex plane and we want to come up with the size of the complex number. So a lot of times people call this absolute value. It's really not absolute value. People say that all the time, but the technical term for this is the modulus. The modulus of a complex number is just its distance from the origin in the complex plane. So let's think about this then. If I'm in the complex plane, and I'm going to go back here just a little bit. Let's go back to like this picture here for a second. If I'm in the complex plane and I'm at this point right here, let's say, okay, and the coordinates of that point I'm not going to specify are just a, b. How can I calculate the distance of that point from the origin? Yeah, Pythagorean theorem. Everybody see that? See, look, if these are the coordinates a, b, doesn't that mean that I've gone horizontally a distance of a, and I've gone vertically a distance of b?
I got this class to get out of geometry.
Well, so what I want you to see here, and I've said this before, is that the distance formula, if you wanted to think about this in terms of a distance, the distance formula is just the Pythagorean theorem, right? All we're saying here is that if this is the modulus, so we'll call that z, the absolute value of z, so that's the modulus, the length of that vector, the distance from the origin, it's just in the Pythagorean relationship, isn't it? We just get z squared equals a squared plus b squared. So how do I solve for z?
You
Square root, right? So I come up with the formula then. The absolute value of z equals the square root of a squared plus b squared, right? And that's just telling me how far away that is from the origin. That's an important thing for us to be able to know. How big of a complex number is it? Jim, question?
So for a complex plane, could you potentially have two imaginary axes?
Two imaginary axes? No. You can't.
So this is like an x and y plane.
Yeah. Yeah. So here's a representation of what I just said. If we want to calculate the distance from the origin to a point, well then, if we use the distance formula, it's just going to be the difference in the x-coordinates. So we end up at a, we started at 0, so a minus 0 is a squared, plus b minus my starting y-coordinate, which is 0 squared. We get the same thing, right? Just the square root of a squared plus b squared. So let's calculate the modulus of a number based on the graph. What's going to be the modulus of this complex number? How far from the origin is it? Yeah, what are the coordinates, first of all?
4, -8.
Okay, so the coordinates are 4, -8. So z, the modulus of z, right, is equal to what?
Square root of 4 minus 8.
No, square root of
4 squared.
4 squared plus
-8.
-8 squared, right? So that's just the square root of 16 plus 64, so the square root of 80. I can simplify that.
40.
No. 5.
Kinda kidding, you're almost there.
5 squared.
Yeah, 4 radical 5, good. Right? That's just the square root of 16 times the square root of 5, and the square root of 16 is 4, right? So this is just equal to 4 radical 5. But we could have done that if we wanted to by making a factor tree out of that, right? We could have done 16 and 5, and 16 breaks into 4 and 4, so I get a couple of 4s and a single 5, right? Okay. What's that tell us? It tells us the size of that number, okay? Okay, so now let's take a look at how we add and subtract complex numbers, and it couldn't be easier. What you're gonna already know. What's your intuition tell you about how I would add up these complex numbers? Treat it like it's an x, and how would I add those two up if I had x's?
You just combine the coefficients.
Combine like terms, right? Combine like terms. I would have, if these were x's, I would have constants and x terms, right? And I would just combine the x terms together, those would be like terms, and the constants would be like terms. So all we get out of this then, let's just underline the like terms in the same colors, right? So we can see that we've got, those are like terms, negative 12 plus 11 is what? Negative 1, okay? And then we get 3i plus 12i is 15i.
So we're adding it?
Yep, you're just adding like terms. You just treat the I like a variable and you add like terms. Okay? Does that make sense? Now, here's my next question for you. Can you make sense of that in terms of that picture that we looked at originally? And this is just like extra stuff. But like if we were to add these two up, if I add those tip to tail, yeah, what am I really doing? Like let's say that we're adding the coordinates up. The coordinates of this first vector were 4 and 3, and the second vector were negative 3 and 2. So if I add those tip to tail, isn't that the same thing as saying I'm going to go 4 to the right, and then when I add this vector, I'm going to go back 3 to the left? Right?
Yeah.
You get that? And so when I add those up tip to tail, I know I'm going to end up in a place that has an x coordinate of 4 plus negative 3, which is 1. Right? When I add this vector to this vector vertically, well, the pink vector means I'm moving vertically by 3, and the green vector means I'm moving vertically by 2. So what's the y coordinate going to be? 5. 3 plus 2. Right? So it does work when we add these things tip to tail. That's the very same thing as just adding like terms in the vector, okay, or in the complex number. Okay, so all we're doing when we're adding complex numbers is just combining like terms. If I have multiple complex numbers, that's no big deal. I just add up all the like terms together from all of the multiple complex numbers. Okay, what if I'm subtracting complex numbers?
You just subtract.
I'm just subtracting like terms. Now, here's one thing I'll recommend though. You're much more likely to make a mistake if you try to do this without distributing. If I try to just do this, if I try to just say, okay, I've got 6 minus negative 13, you might get that first one, but then when you do the second one, and you get negative 7i minus 7i, there's a tendency for people to somewhere in there to add instead of subtract. I just see it every year, right? So what should you probably do instead? Distribute the negative and add. That's it, right? That's all you want to do. So if I distribute the negative, I'm going to get 6 minus 7i. What do I get if I distribute the negative? Plus 13 minus 7i, right? And then all we have to do is just add up like terms. So the 6 plus 13 add to 19 plus negative 7i plus negative 7i would be, okay, and then plus a negative really just means, yeah, I'm getting 19 minus 14i, right? So just distribute the negative and then add like terms, no big deal, okay? So adding and subtracting, piece of cake. It's exactly the way you think it would be. Multiplying is really not that much different either. The one thing we have to remember when we're multiplying complex numbers, you can add this to your notes if you want to. You remind me, what is I squared equal to? If I equals the square root of negative 1, what must I squared equal? Negative 1. There you go, because we're just undoing the square root, right? So I squared is negative 1. And so when we multiply things out, let's take these two examples right here to begin with. Well, this top one is pretty simple, right? What does your intuition tell you would do there? Just distribute the -7, exactly. That's all I do. I just distribute the -7. And I get what? -98 minus 14i. Done. Piece of cake, right? Okay, what about this guy down here? This is a little tougher because now I've got two complex numbers, each of which has a real and an imaginary part. So what am I going to do here? How would you multiply these out if you had x's instead of i's? You just distribute, right? FOIL or whatever you want to call it. It's better just to think of it as distributing. So I would distribute from the first number to the second one, right? Just like you would if you're multiplying out binomials with x's in them. So if I distribute the -7, what do I get? Positive 77 plus 14i. Okay. Let's distribute the 4i. Okay, negative 44i. Everybody agree? Just like those were x's, right? Okay. What's the one thing I got to remember here, though, about the I squared? It equals -1. That's it, right? So all I've got to do is where I used to have an I squared, I'm just going to plug in a -1. So what does that really do to that last term when I have an I squared? Flips the sign, right? Just flips the sign. So then we end up with, I could combine those like terms, and I just get 77, 14i minus 44i is what? Minus 30i. And then what's this become? Plus 8. Combine like terms, and we got it. So there's like terms. So I'm getting 85. And then minus 30i, and I'm done. Question, I saw a hand back here.
Yeah, so say that the 8 wasn't there, and it was negative I squared, then would it be positive one?
Yeah, if it was a negative I squared, then I squared is -1, so you get minus -1 is +1.
So in these kind of good, we're just treating I like you and X.
Except for that one, what I squared you recognize as -1. Otherwise, that's exactly the same. Just the same algebra you would do if you were adding up, if you were multiplying two factors that had x's in them, right? Except for that one difference. I squared you replace with a -1. Okay? All right, so this gets us now, everybody try one of those. I'm going to make one up and just try one real quick. Okay, yeah, you want to just do one on your notes? Do number, real quick, go to page, the bottom of, I guess, page 3 where it says multiplying complex numbers. Why don't you try number 10?
Might be a little bit more.
You work through it. I'll just kind of go through the solution up here and you kind of check along with me.
I'll do that for you.
The 9i when I distributed the I.
Oh, you missed a seven. Yeah, you missed a 6i.
What did I do?
It's 7i.
In the first one, instead of 1 plus I, it's 1 plus 7i.
Oh,
Oh, yeah.
what did I do?
We changed.
Oh, it is.
Yeah, it's,
Yeah, I got, what did I get? 9 plus, that should be a 3i. No,
yeah, that's 3i. And
3i.
then there's
Yeah, I did mess that up.
63.
What did I do?
That is so sad.
So I gotta change everything.
Okay, I want to look calendar that we got something right and do this.
Oh, that's gonna happen frequently, I'm sure. So I got 9 plus 3i, and then I got 9i plus, that, so the rest of it's right, isn't it? So that should be a 12.
No, but the 9 is.
Change the whole thing.
So then I get a 9, is that right?
No.
I got 9i plus 3i squared. Yeah, that's right.
No, you have to, it's
You wrote it
7
down?
plus 7i. 1 plus 7i.
Oh, did I write it down wrong?
Yeah. In the original, I put 1 plus
Oh, I wrote the problem down wrong.
Yeah.
Oh.
1 plus 7.
There you go.
Oh, I see. I got you. Okay, so that messed everything up. So here's what the answer should be on that.
Is it 64I minus?
Are we out here in 1 minute?
Yeah.
Oh, okay. So I'll just look it up real quick.